today's class. Now I'm going to revisit simple transitivity of on triples of distinct points, but using linear algebra. Okay, so I'm going to try and see it as a P1 shadow of the theorem of linear algebra that tells me that if I'm given a basis of a vector space, then for every function from that basis to another vector space, there is exactly one linear map that extends it. Right? Okay, I'm going to try to see the simple transitivity as a P1 shadow of that. Then I'm going to discuss kind of the fundamental invariant for Möbius transformations, which is the cross ratio. And later I'm going to compute explicitly the fixed points of a Möbius transformation in terms of the entries of any of the matrices that represent it. And finally, I'm going to establish some relation somehow between the, let's say, the algebra, between the possible algebraic relation, a possible algebraic relation between two Möbius transformations, and kind of something which is kind of more geometric, which are their fixed points. So let's talk a little bit about simple transitivity by means of linear algebra. So as I said, for any given basis, let's say of C2, for the moment, I mean, it suffices to me to consider just C2 and any given basis of this very particular vector space. Every function from the basis can be extended in a unique way to a whole linear map from the whole space of which B is basis. Right? So, okay. So, and now I'm going to try to see simple transitivity as the P1 shadow of this theorem. Okay. Have you all seen this theorem in linear algebra? I mean, usually one proves like a much more general version, right? Yeah. Okay. So this is just a reminder of what the statement is of the theorem on simple transitivity of the action of Möb C bar on triples of distinct points of C bar. And now last time, like the previous proof I gave, which was kind of to compute completely explicitly one such Möbius transformation. In the previous proof, I said it suffices to show the theorem in the special case where these ones, Z1, Z2, and Z3, were 0, 1, infinity. Well, now with the kind of the new proof, the new perspective I'm going to give, I'm going to do it in this case, but now where the other points are supposed to be like these special points. The reason why it suffices is really the same. Why it suffices to prove the theorem in this case is really the same I said last time. So I'm just going to embark into the proof. So take the standard basis of C2. Right? So E1 is just the vector 1, 0. E2 is the vector 0, 1. Okay. And then recall this bijection. The bijection from C bar to the complex projective line, written in terms of this basis, right? So it's kind of the parametrization of P1C by complex numbers union infinity, using with respect to this basis, right? So Z goes to this one-dimensional vector subspace, and if Z is a complex number, and infinity goes to this other one, right? Okay, and now notice I'm taking my points W1, W2, W3 to be infinity, 0, 1, and then infinity goes to this vector subspace, right? So which is just the subspace spanned by E1. 0 0 goes to, well, 0 is a complex number, and then 0 goes then to this vector subspace, which is just the subspace spanned by E2. And finally, 1, which is a complex number 1, goes to this other vector subspace, the one spanned by the sum. Okay, so that's just clear from this formula. Okay, and now what I'm going to do, you see, now I recall I have these points which I am assuming are these special points, but I also have the other points which I don't forget about them, right? Z1, Z2, Z3, and of course these points go onto certain subspaces by this function, right? So phi of Z1 is a one-dimensional vector subspace of C2. Same thing for phi of Z2, and same thing for phi of Z3. Okay, and as such, being each one of them a one-dimensional vector subspace, I can pick a non-zero vector inside it. Right? So I pick a non-zero vector inside each of them. Okay, and now I notice the following. I'm assuming that Z1 and Z2 are different. So since this function is bijective, phi of Z1 and phi of Z2 are different. Right? They are different one-dimensional subspaces of C2. And being different, so this one being different to this one, you see, it means that V1 and V2 are not linearly dependent. They cannot be, right? Because they really span different vector subspaces. And being linearly independent, well, then they form a basis, right? It's a linearly independent subset consisting of two vectors. It's automatically a basis. So I can write the third one, V3, as a complex linear combination of V1 and V2. Okay, now Z3 is different from Z1 and Z2, right? Because it's Z1, Z2, Z3 is a triple of three distinct points. Okay, so Z1 is not this and it is not this. So alpha and beta are not zero, because say if beta were zero, then V3 would be in the same one-dimensional subspace as V1, but then this one would be equal to this one. And similarly, if alpha were zero, then the vector subspace spanned by V3 would be the vector subspace spanned by V2, and then this would be equal to this one, but they are not. Okay, so these are alpha and beta are different from zero. Okay, and now comes the fundamental theorem of linear algebra, because there is exactly one C-linear map sending the first standard basis vector to this one, and this one to this one, right? So you see, the point is that I want to send infinity to Z1 and 0 to Z2. That is why I decide to send E1 to something in this space and E2 to something in this space, right? But somehow I want to do it in a controlled manner. Because I want also to send 1 to B3. That is, I want to send E1 plus E2 to a multiple of B3. Right? So somehow it's kind of, I want somehow, if you see, I could have said send E1 to V1 and E2 to V2. Yeah, but somehow I'm using the fact that I can rescale without changing the subspace and rescale without changing the subspace, kind of, so that the parallelogram law, right, kind of gives me the correct one, the correct point. This I'm going to show up some animation later. So that, yeah, so okay, because you see, now I have what I want, which is this the vector subspace spanned by this one is V of Z1, right? The vector space span, the vector subspace spanned by F2 by F of E2 is this one, so it's the correct one. And now this one really hits the vector space spanned by B3. Okay, so yeah, okay. And I would say, from there I can kind of already if I already have like some practice, if I'm already used to kind of just passing between C bar and P1 kind of by means of this phi with respect to this basis, just from here I can already say, okay, so your Möbius transformation satisfies that infinity goes to Z1, 0 goes to Z2, and 1 goes to Z3. Right? But okay, but I'm going to just perform the computation slowly. So I take the matrix representing the linear map with respect to the standard, with respect to the, let me see, with respect to the standard basis, yeah. So, okay, and now I compute, right? When I write f of E1, just by basic linear algebra, is this one times E1 plus this one times E2, right? And the f of the second standard basis vector is b of E1 plus d of E2, right? Just basic linear algebra. And moreover, f of E1 plus F2, well, just direct computation, right? It's kind of because of linearity, if you want, it's this plus this. Right? So I factors, and it's a plus b, and I factor E2, and it's c plus d. Okay, but then you see, when I compute the Möbius transformation associated to this matrix, and then I check in infinity, where does it go? Well, it goes to A divided by C. To A divided by C. But A divided by C, you see, consider this one, and you see A divided by C is precisely what you obtain when you perform this trick of dividing by the second entry, right? To just go back to C bar, right? To go from from P1C back to C bar with respect to the basis B. Right? So this is what I'm saying. But this one is just Z1, right? I mean, where is it? You see, when I apply phi inverse, I get Z1. So phi inverse gives me Z1. Similarly, mu of 0. Well, I check here, and then I have to plug in, 0. So it's b divided by d, b divided by d. B divided. So you see, b divided by d. Same thing. It's precisely what I obtain when I apply the trick of dividing by the second coefficient. So it's phi inverse of this one. But this one is Z2. It's just here, right? When I apply phi b inverse, I get Z2. And finally, for 1, I plug in 1. So I get A plus B divided by C plus D. Okay, but then that's, you see, it's precisely what I obtain by applying the same trick, dividing by the second coefficient. Okay, and again, this really gives me Z3. Okay, so this means that this Möbius transformation does what I want, right? It sends infinity to Z1, 0 to Z2, 1 to Z3. Okay. Now, of course, I know that that different matrices can give me the same Möbius transformation, right? But so anyway, so let me go into the uniqueness part, and so what am I trying to say? So here, notice when I chose this linear transformation, I could have chosen, for instance, just a non-zero multiple of it. Right? I mean, I could have chosen instead of this f, I could have chosen, let's say, 2 times this f. And then 2 times this f would have sent me here. But I would still have landed in the correct vector subspace here. Right? And the sum would be, you see here f of E1 plus E2 would be 2 times alpha V1 plus 2 times beta V2. So I would still have landed in the correct subspaces, right? So what I'm saying is, if I rescale the linear transformation, I still have I'm still getting a Möbius transformation that does what I want, right? But if it's only rescaling, right, then this is what happens, and then I see that it's the same Möbius transformation, right? And somehow my point is now that the argument that I'm about to give really is the argument that corresponds to the following. If you take 2 vectors and then consider the parallelogram kind of they generate or they span, you see, and then you cut with one line. When you start rescaling, let's say, if you rescale both, kind of you get the same, you get the same point. You can get the same point in this line that you put many times. Okay, but but then so then I just fix one parameter, fix one of them, and then allow to rescale only the other one, so that I hit everything only once. And that's somehow the point. The argument I'm about to give is that really, if instead of allowing to rescale both vectors, you are allowed to rescale only one of them, when you consider the parallelogram, the parallelogram that this one and a non-zero multiple of this one span, the resultant cuts exactly, there's only one way to cut each point of this line. Okay, so I'm going to give this argument, and then I'm going to show you what I just said, kind of in a small program, which is also kind of easier than just moving hands, right? So for the uniqueness, take any linear map that does what you want, right? So that it sends E1 to a multiple of V1, E2 to a multiple of B2, and E1 plus E2 to a multiple of B3, right? Lambda 1, lambda 2, lambda 3. And what I would like is to show that this G is necessarily a rescaling of F, so that it's a non-zero multiple of F. That's what I want, right? Because then I know that the Möbius transformations are really the same, and so I can deduce uniqueness. Okay, but then you see V1 from the previous one that I defined, V1 is really alpha inverse times this one, and here I'm using that I know that alpha was not 0. Right? Remember that we stressed that alpha and beta are not 0. So now it's when I'm using it. So V1 is alpha inverse this, V2 is beta inverse this. So I write it. So in these equations, I simply replace V1 by alpha inverse f of E1, V2 by beta inverse f of E2, and V3 is really f of E1 plus f of E2. So I just write it. Right, and then by linearity, I can just open this sum and then distribute lambda 3. Okay, but then you see, this is on the one hand, because I replaced the V3. On the other hand, this plus this also gives me this, right? So it must be, and f of E1, f of E2, they are linearly independent. So when I add these two, it should really give me lambda 1 alpha inverse should be lambda 3, and lambda 2 beta inverse should also be lambda 3. Yeah. So I write it, and then you see I can solve for lambda 2. You see lambda 2 is then well, lambda 1 alpha inverse times beta, of course. And then I go back, right? Then I go back here, and kind of just to check these two, right? It's enough to check that I mean, G is determined by what it does in a basis. Okay, so I go back here, and then I plug in lambda 2, right? Lambda 2. So G of E2 is lambda 2 times beta inverse f of E2, beta inverse f of E2. And beta inverse goes away. And you see what I have just shown is that then G is this scalar multiple of f. So they give me the same Möbius transformation. Okay. Yeah. So let me show you this. This is actually kind of the same program that we saw the other class. And you see, in the first class, I told you, I don't know, the other day I told you, ignore the red and blue lines and focus only on the green line, right? But kind of today, what I've just shown is kind of, I just focus precisely on the red lines and the blue lines. And here you can see the parallelogram I was talking about. Yeah, and then here, this is my f of B2, sorry, f of B1, this point that you are seeing here. Oh, this point that you are seeing here. This is f of B2. And of course, this is f of E1. Sorry, I said V1 and B2, right? Sorry, this is f of E1. This is f of E2. And this is f of E1 plus E2. But you see, C bar, or P1C is really sitting here. And actually what we are seeing is only P1R, right? And then somehow the Möbius in the end, the Möbius transformation, oops, let me see. You see the Möbius transformation is always sending which one? I think it's 0. I will have to rethink. 0 goes to this point. 0 goes to this point. Infinity. Sorry, no, not 0. That's infinity. Infinity goes to this point where this red line crosses the blue line. That's infinity. Yeah. 1 goes to this point. Sorry, not 1. 0. 0 goes to this point, and 1 goes to this point. And you see, when I start rescaling, somehow the image of the first point doesn't change because I'm not changing this subspace. The image of the second is not changing because I'm not changing the subspace, but somehow, you see, what I'm allowing to change is precisely just the image of the third point, right, which is just this crossing point. Okay? Right, and then, so you see the uniqueness of the Möbius transformation really corresponds to the fact that when I pick one of these two vectors and rescale it, but not rescaling the other one, I start hitting. I hit each point in the blue line precisely once. That's the statement of uniqueness. Okay. Okay, so let's go back. And now let me speak about the cross ratio, which is kind of the invariant, the most fundamental invariant for Möbius transformations. And so let me start with kind of just with the problem of finding invariant functions, right? Which kind of this what we are about to see is kind of it's a baby version of problems that appear kind of that it's kind of actually a whole area of research nowadays. But so now what we're going to see is kind of just a super baby examples. So let's say that I want to determine all the functions, or if you want holomorphic functions from C bar to C bar, which are invariant under Möbius transformations. That is, you see that the value of f the value of f at any point is equal to the value of f at the image of that point under a Möbius transformation, and that this holds for every Möbius transformation. Okay. Well, I know that any 2 points in C bar can be related by a Möbius transformation. Right? Actually, by many of them. Right? I mean, actually, that's the exercise that I showed at the beginning of the class. That has to be handed in next time, right? To compute all the matrices that take one to the other. So for any 2 points in C bar, I can find at least one Möbius transformation that takes one to the other, right? And then the Möbius transformation the value of any such f here has to be the value of f here, right? But then for any other point, the value there, it has to be the value here, right? So the value at any point in C bar has to be just the value at that given point. So the function has to be constant. Right? So only the constant functions from C bar to C bar are invariant under the action of the Möbius group. Now, well, then I add one more variable, right? And now I want to determine all the functions, or if you want to think about holomorphic functions of more than one variable, if you are kind of already comfortable thinking about them, then think about them. That are invariant under, again, the action of the Möbius group. Now the point here is that I have certain action of the Möbius group here as follows. Somehow the point is that any Möbius transformation can be applied to any pair of elements of C bar, right? So I can say f star nu of z1, z2, that this be f of nu of z1, nu of z2, right? And what I obtain is this. Oops, this is again a function of two variables, right? And then and then what this gives me is a right action of the Möbius group on the set of all functions from C bar square to C bar. And then I ask myself, what are all the invariant functions for this action of the Möbius group? And the answer is again only the constant functions, because again, if you give me two ordered pairs of distinct points in C bar, there is at least one Möbius transformation connecting them. So the value of the function has to really be constant. Okay. Here you have to use continuity. So this you see, if you are not used to thinking about holomorphic functions in several variables, put here at least continuity. Okay, because somehow I'm arguing for pairs of distinct points, and in the set of pairs of distinct points, it has to be constant, and then by continuity, it has to be constant in the whole of C bar square. Then you imagine. Then you can already see. Okay, one more variable. Still, and the answer still, and you see the same question. Find all the invariant functions from C bar cube to C bar that are invariant under the action of the Möbius group. Again, only the constant functions, because of the simple transitivity in triples of points. Right? If you give me two triples of distinct points, there is one Möbius transformation taking this to first one to first one, second one to second one, third one to third one. So the value of the function, at least on the set of all of triples of distinct points, has to be constant, and by continuity, it really has to be constant in the whole C bar cube. Okay, so only the constant functions, and now the story starts to be interesting when I have four variables. Because now it is not true that if you give me two quadruples of distinct points, there exists a Möbius transformation sending one to the other always. Right? Because think about, you see, take two quadruples of distinct points. Okay, and then limit your attention to only the first three and the first three. There is exactly one Möbius transformation taking the first one to the first one, the second one to the second one, the third one to the third one. And this unique Möbius transformation has already some behavior at this point. And that point is sent somewhere. Right? It's sent somewhere. Does it have to be this one? Well, not necessarily. Right? So this means that the unique Möbius transformation that has the desired behavior in the first three may fail to have the desired behavior in the fourth one. Right? So it is not always true. It is not true that for every pair of quadruples of distinct points there is one Möbius transformation sending one to the other. That fails, right? And the reason why it fails is because for triples it was unique. Okay. So now the answer then we should expect the answer of finding the invariant functions to be more interesting than in the previous cases, right? One variable, two variables, three variables. All right. Now, any such function invariant under all Möbius transformations, well, of course, it has to satisfy this equality, right? For all points, and for all Möbius transformations. Right? In particular, you see, for the unique Möbius transformation, so if you want, fix this quadruple of points, yeah? And consider the unique Möbius transformation sending the second one to 0, the third one to 1, and the fourth one to infinity. We know there is exactly one, right? So here I'm focusing on the last three. Okay, right, and it has some value at W1, right? Okay, it has some value at W1. Okay, and then since we must have this, well, f of W1, W2, W3, W4 has to be equal to f of applying this sigma, right? Well, in the second one, I get 0. In the third one, I get 1. In the fourth one, I get infinity. And here I get sigma, f of sigma of 1, of W1. Okay, so this means that for this function of 4 variables, so from C bar to the fourth to C bar, defined by this rule, right? Rho of a quadruple to be the value of this Möbius transformation at the first point. We have a commutative diagram of, at least of continuous functions, if you are already used to thinking about holomorphic functions of several variables, think about that. Otherwise, it's at least continuous functions, right? Such that you see if the value of f at any point is determined by the value of f at the image of this quadruple under rho. So in other words, what I'm seeing is that any such f, you see, any such f can be written as the composition of rho with some function of one variable. These people used to say that f factors through rho. And so what this tells me is that then the invariant functions really kind of are just kind of this. They factor through rho and through just the holomorphic functions from C bar to C bar. In other words, this function allows me to find all possible invariant functions, not invariant functions. So I give it a name. It's the cross ratio. For sure, one must be able to give a formula for that one, right? Because we know we are defining it as sending W2 to 0, W3 to 1, and W4 to infinity, right? And for that we have some formulas from last class, and then in that formula we just plug in W1. Right? So the formula has to look like some coefficient, some in general, kind of as a product of something like this, right? Let's see, something like this, depending on whether W2, W3, W4 are infinity or not, but it has to look something like W2 to 0, so W1 minus W2, and then W3 goes to 1, so W4 goes to infinity, so W4, then W1, and then W3 goes to 1, so it has to be W3 minus W4, W3 minus W2. So, for instance, if W1, W2, W3, W4, if none of them is infinity, this is the formula for the cross ratio. Right? So here, what I want you to see is that I just need to remember how to produce the desired behavior of a Möbius transformation, and then I can come up with a formula. Okay, which is not usually what you find in the books, right? So what you find in the books usually is just the formula, right? But it doesn't tell you, okay, where did it come from? yeah, I only wanted to motivate the appearance of the cross ratio from the problem of finding the invariant functions. Okay, and of course the fact that somehow, yeah, that I'm introducing this function is kind of a similar reasoning, right? That doesn't mean that this one is already invariant. Kind of similar to what you just said, and that's the theorem that the cross ratio is holomorphic and invariant under the action of the Möbius group. And by Möb invariant, what I mean is kind of just to be completely clear, is that rho of a quadruple is always equal to rho of the images of the quadruple under any Möbius transformation. Okay, and the proof, I'm going to leave it as an exercise, right? The proof of this theorem. Okay, and then you can say, okay, so what, right? I mean, okay, the cross ratio appears from the problem of finding invariant functions, but so what, right? I mean, is it really useful? And somehow the point is that it is actually useful. Suppose that I am given 4 distinct points in C bar, and right, and then someone asks me, okay, do they lie on a circle or not? And then, of course, something I can do is kind of to draw the mediatrices for two of them, and then draw the circle that passes through three of them, and then check whether it passes through the fourth one or not. Right. So I know that the problem, I know how to solve it. Right? But then somehow I would like to have some way of answering quickly, right? Like okay, so some way that maybe just with some basic algebraic computations, someone tells me, okay, so are these 4 do these 4 lie on a circle? Right? And then I say, okay, just plug in somewhere in some calculator or something, and then say yes or no. Right? And that's precisely what the cross ratio allows me to do, because you see, if I take 4 distinct points on R bar, let me think. Yeah, no, just think about the following. Consider only the points 0, 1, infinity in R bar, right? In the real numbers union infinity. The real numbers union infinity are a circle in C bar, right? Because it's a straight line union infinity. Okay, now I have my 3 points 0, 1, infinity, right? And then consider a fourth point, which would be kind of my W1, really. Yeah, and then take the Möbius transformation that sends 0 to 0, 1 to 1, infinity to infinity. Well, it sends this one to itself, which is a real number. Right? And this one, of course, lies on this circle. And reciprocally, if I take something outside R bar, it's a complex number with the non-zero imaginary part, and this Möbius transformation, which would be the identity, kind of sends it to itself, so it has a non-zero imaginary part, and it doesn't lie on this circle. So now take any quadruple of distinct points and send 3 of them to 0, 1, infinity, which is what I'm doing here, right? This is how I define the cross ratio. Right? And then take the value of the fourth one. If it falls in R bar, right, the cross ratio is real, and this means that the original one lies on the circle determined by the other 3. And if the image is not in R bar, well, it has non-zero imaginary part. It's not real, and this means that in the original one, the fourth point did not lie in the circle determined by the first 3 points, but by the other 3 points. right? So what I have is that 4 distinct points lie on a circle if and only if their cross ratio is a real number. And the cross ratio really gives me an easy way to decide whether any 4 given points are lie on a circle. All right, so let me move on to computing fixed points explicitly. We know that every Möbius transformation has at most 2 fixed points. Right? So we have any non-identity, any Möbius transformation, which is not the identity function of C bar, has at most 2 fixed points. This fact then presents me 2 problems. The first problem is, okay, is it true that every Möbius transformation has at least 1 fixed point? And the second problem is, okay, how do you find them explicitly? Right? Say that someone gives you a 2 by 2 invertible matrix and asks you, okay, so what are the fixed points of the Möbius transformation? We're going to solve both of these problems, and the answer is just going to be, the usual quadratic formula for solving a polynomial of degree 2. Yeah. So here, as I said, take an invertible matrix, right, and then just take it. Take a matrix which is invertible, but that from which you know that it doesn't give you the identity Möbius transformation. So suppose that it's not a multiple of the identity, right? So this is just to exclude the identity Möbius transformation, right? Well, the first thing, infinity goes to infinity if and only if gamma is 0. This is right? Because somehow this one, this we said it was going to be alpha divided by gamma, right? And this one is infinity precisely when gamma is 0. Okay, so that's kind of the first thing we do. We check, is gamma 0 or not? Because if it's 0, we already found a fixed point. Infinity goes to itself. It's fixed. Okay, and so we divide into 2 cases. When gamma is 0, where okay, maybe we can find more fixed points, right? Or when gamma is not 0, in which case we haven't even found any fixed points yet. So let's analyze what happens in the first case when gamma is 0. As I said, then infinity is a fixed point. And then finding any other fixed point, well, you see, what do? I plug into the formula, right? I mean, if gamma is 0, I know that the formula is z goes to alpha z plus beta divided by gamma z plus delta. And I want this to be equal to z, right? So what I want is find the solutions of this equation. Now notice, this may fail to have solutions. Like, for instance, if alpha is equal to delta, then this kind of just cancels, and then there is no solution. Okay, but if this is different from 1, there is a solution. And how do I find the solution? Well, I just solve, right? Kind of just high school algebra. Okay, and then I have this fixed point, and then what I see is that if gamma is 0, then I have at most 2 fixed points. There are exactly 2 fixed points if alpha and delta are different, right? And in that case, the 2 fixed points are infinity and this other one. Okay, and if alpha is equal to delta, infinity is the only fixed point. Okay, that that finishes the analysis in the case gamma equal to 0. Let's move on to the other case, which kind of just as a reality check. The second case kind of is more generic. It dominates over the first case, because if I pick a matrix randomly, it is the most likely fact. It will be most likely here non-zero. Right? So really the second case is kind of really the interesting one somehow. Okay, if gamma is not 0, then infinity is not a fixed point, right? Because mu a of infinity is alpha divided by gamma, and since gamma is not 0, this is not infinity, definitely. So mu of infinity is not infinity. Okay, so this is not a fixed point, and moreover, notice here I have this complex number. This is definitely a complex number, right? And mu a of that complex number minus delta divided by gamma. So notice here is alpha times such thing divided by gamma minus delta divided by gamma plus delta. So this is 0, so this is infinity. So this complex number goes to infinity, so it's not fixed. It's not fixed because it doesn't go to it goes to infinity, it goes somewhere else, right? So infinity and this point are not fixed points in this case. And finding the fixed points, well, a fixed point must satisfy that this expression is equal to itself, to z itself, right? So that z is actually fixed by the expression. Okay, but then the solutions of this are the solutions of this. So one really has to, you see, kind of just collecting things on the left. One really it becomes finding the solutions of this polynomial. This polynomial, which has degree 2 because gamma is not 0, right? Has degree 2. Now, degree 2, so it has at most 2 roots, but it may have only one, right? It may have only one if the discriminant vanishes, right? But in any case, finding the solutions of the roots of a polynomial of degree 2, well, this we know since secondary school, right? Or maybe even before. It's just the quadratic formula. And so there is exactly one fixed point if the discriminant, which is this, what is inside the square root symbol, vanishes. And in that case, the only fixed point here is the computation. And there are exactly 2 fixed points precisely when that discriminant is not 0, in which case the two fixed points correspond to taking plus on the one hand and minus on the other. And then that finishes all the cases. So what we see is, if we are given the matrix giving rise to our Möbius transformation, we can compute explicitly all the fixed points in terms of the entries of the matrix, right? And kind of the only basic kind of difference that we have to make, the only basic consideration we have to make is whether gamma is 0 or not. Okay, so kind of we first ask ourselves, is gamma 0 or not? If it is, I have a fixed point. I try to find more. There will be at most one. If gamma is not 0, from this expression, I cook up a polynomial of degree 2, find its roots, and from the vanishing of this, I obtain that there is only one or there are 2 roots. Okay, and finally, now that we are speaking about fixed points, which really has to do with the geometry of the Möbius transformation, let's see how it connects to commutativity. So there is something very nice that happens. So let's denote. Let's give some notation for the set of fixed points. Right? So just fix of nu in C bar. And more generally, notice if I'm given a set and any bijective function, I can define fix of the bijective function, right? Bijective function from x to x, fix the fixed points in x, right? And then I can define same thing, right? The points in x fixed by my bijective function. Right? Okay, so this really is kind of part of a kind of something that I can do in general. Exercise. There is this very nice relation. You see, if I take two bijective functions and I conjugate one with the other, the fixed points of this conjugation coincide with the image under G of the fixed points of f before being conjugated. So this is a very, very, very beautiful formula, in my opinion. So I leave it as an exercise. It's very easy. It's not hard. And notice it has this consequence, which is if f and g commute, right? If f and g that f and g commute is equivalent to g preceded by f preceded by g inverse to be equal to f, right? So f and g commute if and only if the result of conjugating f with g is f itself, right? Okay, if they commute, since this then becomes f, then g simply permutes the elements of fixed f. Right? So if two commute, then one permutes the fixed points of the other. Okay, and well, now we're going to use that to show that if you give me two Möbius transformations, it happens that they commute precisely when their fixed points are the same. Precisely the same set of fixed points. Yeah. So let's prove it. Suppose they commute. Then, as I said, one permutes the fixed points of the other. One permutes the fixed points of the other. Right. So it goes both ways. If they commute, it goes both ways. One commutes the fixed points of the other, but the other way, the other also permutes the fixed points of the first one. Right. Okay, and now we divide into cases, because being Möbius transformations, sigma has either exactly one or exactly two fixed points. Okay, because I take them to be different from the identity Möbius transformation. Okay, now case one, suppose that sigma has exactly one fixed point. Yeah, I mean this symbol is cardinality symbol, right? The symbol for cardinality of a set. Okay, so since tau permutes this set because they commute, and since this one has exactly one point, notice tau of that point has to be that point, because tau permutes this one element set. So tau of that point has to be that point. This means that this point is fixed by tau. That is, this set is contained in fix of tau. Okay, but now you see, then this cannot have two elements. Why? Because sigma, let's suppose that it has two elements. Let's see what happens. Well, sigma permutes those 2 points, but already fixes one of them. So it has to fix the other. But then it has to fix points in contradiction to this. So this possibility is really not a possibility. So tau must have exactly one fixed point. Exactly one fixed point. So these two are sets with exactly one element, one containing the other. They are equal. Okay. Case 2. Suppose that sigma has exactly two fixed points. Right? Recall that I'm assuming that they are commute. Okay. Then tau must have two fixed points because of this case. If it had only one, then I would be able to deduce that sigma also has only one. Right? I mean, kind of just just inverting exchanging the roles of sigma and tau here. If tau had exactly one fixed point, then here exchanging tau and sigma, I would be able to deduce that the other one has also one fixed point, but the other one is sigma. So this must be the case, that if sigma has two fixed points, then tau must have two fixed points, because the previous case is already written on stone, right? Okay, so let's write fix of sigma, right? Z1, Z2. Let's say that Z1 and Z2 are the two distinct points, the two distinct fixed points of sigma. I want to show, you see, I want to show that this set is contained in fixed of tau, because I want to show that the two sets are equal. So let's suppose not, and see what happens, right? So let's suppose that the first one, say, is not fixed by this one. Okay, then what happens? You see, tau permutes this set because they commute, because tau and sigma commute. So tau permutes this set and does not fix Z1. So it cannot fix Z2 because tau is bijective, right? So it must be doing this, just exchanging them. But then in particular, Z2 is also not fixed. Okay, now it permutes them, right? So when I apply tau once, it exchanges them. When I apply tau again, it goes back. So tau square fixes both. Okay, now notice if something is already fixed by tau, it's also fixed by tau square. Right? If it's fixed by tau, then it's fixed by tau square. Okay, now these two belong to this set, and this set is also contained in this set. But you see, this point is not here, and this point is not here, and this guy has at least 2 points. So Z1, Z2, and the 2 points here, they are 4 distinct points that belong here. So tau square must be the identity because it fixes at least 4 points. So tau square is the identity, right? I mean, okay, tau square is the identity, but for instance, rotation, let's say, for instance, 1 over z is not the identity, and its square is the identity. So I'm not done yet. Okay, but something I can do is the following. I have the 2 fixed points of tau, and I can take some Möbius transformation that takes one of them to 0 and the other one to infinity. And actually, even I can do that, and I still have 1 degree of freedom from the transitivity of triples. So I can definitely send one of the 2 fixed points to 0 and the other one to infinity. And when I do that, because of this formula, you see, when I send them, I'm actually computing the fixed points of the conjugate. So when I send them with nu to 0 and infinity, I'm computing the fixed points of the conjugate. Okay? Okay. Right. And then you see this one, it's, again, its square is the identity, right? Because you see, just compute the square of this one. Right? I mean, the square of that one is nu tau nu inverse nu tau nu inverse. So I get nu tau square nu inverse, and tau square is the identity. So this is nu inverse is the identity. Right? So this one, its square is equal to 0. Right? Square is equal to 0. No, sorry, its square is equal to the identity. And it fixes 0, and it fixes infinity. Again, it fixes them because of this formula. Okay. Right. So I have a Möbius transformation of order 2 fixing 0 and infinity. So let's see. Let's say that this one is given by some matrix, right? A, B, C, D. Not alpha, beta, gamma, delta, A, B, C, D. It fixes 0. So if you want, it fixes infinity. So C has to be 0. So it actually has this form. It fixes 0. So B has to be 0. And its square is the identity. So A square 0, 0, D square. This one is plus or minus the identity. Let me say it more correctly. Yeah, I mean, I can take this one actually in SL2C, as we saw last time. Every Möbius transformation can be represented not only by a matrix in GL2C, but actually by a matrix of determinant 1. And the fact that this square is the identity tells me this square is in the kernel of the group homomorphism that to which matrix associates its Möbius transformation. So this one is plus or minus the identity, because I'm assuming determinant 1. So this is plus minus 1, 1, 0. Right. And right, and AD is equal to 1. So really this is A inverse. And A square is plus or minus 1. Right. Right, but A square is plus or minus 1. Let's say I can assume without loss of generality that A square is 1. Let me see, I'm getting a bit lost. Right. Yeah. So I noticed the following. When I take, I mean, since this one fixes 0 and infinity, I note that whenever I take a matrix that represents it, this matrix must have this form. It must be 0 and 0 here. So this one becomes multiplying by a divided by d. I mean, z goes to az plus 0 divided by 0 plus d. So z goes to z multiplied with a divided by d. Okay? And we know that this one square is the identity, because tau square is the identity. This I already showed you the computation. So when I consider, so this one is multiplying by something, namely a divided by d, and multiplying by a divided by d square is just multiplying by 1 because it's the identity. So a divided by d square is equal to 1. Yeah. Okay. But tau is not the identity because it doesn't fix z1. So this one is not the identity. So this one is multiplying, this one is the same as multiplying by something whose square is equal to 1, but not equal to 1, so minus 1. So this one is multiplication by minus 1. Okay. Is it clear? Was the reasoning clear? Yes. Okay. Okay. Now, now I take. You see, I take the same nu here, but now I conjugate sigma. Here I was conjugating tau. Now I'm conjugating sigma. Right? And then I take any matrix representing this conjugation of sigma. Now, since sigma and tau commute, that hypothesis I have not used yet in this case too. Well, I used it to show that tau has two fixed points, but okay, but I use it again then. We have, notice, this is by definition just this applied to z. Okay, that applied to z. For this one, something I can do is, you see, I can write nu sigma nu inverse. Let me see. Right, sorry. So you see here to this, something I can do is nu tau inverse sigma nu inverse, and it's the same, right? Because I just wrote tau inverse. So okay, but then since tau and sigma commute, I can pass tau to the right of sigma, tau inverse to the right of sigma, and then this is equal to this equal to this. Okay, just because they commute. Okay. Now you see here. Here I can write this as nu tau tau sigma nu inverse nu tau minus 1 nu inverse of z. Right. You see, and here you see this one is multiplication by minus 1, and so its inverse is also multiplication by minus 1. Okay, so this is just multiplying z with minus 1. Right? So, and then then I can erase this. Yeah, and then I only this remains. Okay, and now I can write here. I can write this as nu tau nu inverse nu sigma nu inverse. right, of minus z, right, and then this I can control with my matrix, right, and I have to apply that matrix to minus z, and which matrix? This matrix that I wrote here before. So I take minus z, and then I plug it in the formula, yeah. And then I can erase this, and this remains. Yeah, but then this is again multiplication by minus 1. So I have to take this and multiply by minus 1. So I obtain this. Yeah, and what do I see? What I see is that you see this is equal to this, right? So the Möbius transformation is equal to the Möbius transformation of this other matrix, right? So you see, one has to be, let's say A has to be a non-zero scalar multiple of this one, right? But you see, you have alpha and alpha in the as first entry, gamma and gamma also they coincide, so these two have to be 0. But if they are 0, the matrix was not invertible. Okay, so what must be happening? I mean, from this assumption, we arrived at a matrix that is at the same time invertible and not invertible. That's a contradiction. So it must be the case that Z1 really belongs here. And for similar reasons, Z2 must also belong here. So I must have this containment. So the two sets have to be equal. Yeah. Okay. And then my time is up. So next class I just finish the converse. That if they have the same fixed points, the same sets of fixed points, then they commute. And then just also to hand in, when is it? The next week, this exercise. Okay. Compute the set of fixed points of these Möbius transformations given by these matrices. Okay. All right, and then I'll see you next Wednesday.